All right, welcome. So in this video, I want to continue doing some pumping lemma proofs to show that languages are not regular. And I'm going to start with this language here, L. Let's take a quick look at this language. We'll notice that it's in a similar form to some of the languages we've looked at already. We've got a block of zeros and a block of ones, and we have two variables, n and m, defining how big they are. And in this case, we're defining some relationship between n and m. So we're saying that there needs to be more ones than there are zeros. So we've got sort of n is greater than or equal to 0, so it could be 0. M is greater than or equal to n, so it could also be 0. So I guess I said it has to have more than n. That's not exactly right. It could be equal to or more ones than 0. Okay, so now we're going to try and use the pumping lemma to prove that this language is not regular. Okay, so to begin our proof, remember that when we're using the pumping lemma, proofs with the pumping lemma are proofs by contradiction. We're going to assume that L is regular, and therefore the pumping lemma should tell us that there's certain properties that this language will have. Then we can show that those properties don't hold, and that will be the contradiction we get. So let's begin with our assumption. Okay, so we begin by saying let's assume L is regular, and therefore the pumping lemma should hold. And now our next step is going to be to try and pick some string S that's going to be a member of the language L, and that is going to allow us to hopefully make some kind of argument with our pumping lemma. Now, remember, when we're doing this, we usually, if we have these two blocks or if we have these variables, if we have, say, a variable n, we might plug in p, the pumping length, in to ensure that our string is long enough. And then we're going to have to pick maybe a potentially different value for m, noticing here that m has to be greater than or equal to n. So in this case, whatever value we pick here must be greater than or equal to p. I don't have any good reason to pick something greater than p, so I'm just going to pick p again, and hopefully that's going to work. Now remember, sometimes when we pick a string like this the first time, it's not going to work for us, or it might work, or it might not, and we might not figure that out until we finish making our argument down below. It's perfectly okay for us to return back to this string afterwards and say maybe we were wrong there, maybe we needed a +1 on here or something else that will help us make this particular language show that it is not regular. But my instinct is, let's try the simplest thing first. So that's why I said I don't have really a good reason to pick anything bigger than p, so let's pick p and see if it works. It's the simplest one I could pick. So I'm pretty satisfied with this particular s. I'm just going to say let s be equal to this string, and I'm just going to happen to note, hey, notice this is in our language L. These are the important things. And maybe I'll make one other note, which is that the length of s is greater than or equal to p. Remember, this is also important for us to apply the pumping lemma. So the pumping lemma says for any strings that are larger than the pumping length out of the language, we can pump them. And so that's what we've got here. So now we're going to move on with the three properties. So our three properties tell us, or are about, our string s after we divide it into potentially these three substrings x, y, z. And remember, there are a couple properties about these. And usually these properties, if you've got a little bit of instinct from our previous examples now, what we're trying to do is argue about what's going on in y, the substring y, because that's eventually the one that we're going to pump. So I'm going to start by mentioning that since the length of xy must be less than or equal to p, that means the xy component of our string here must be all part of this block of zeros. And in particular, that means the string y, the one that we're concerned with, must only have zeros in it. And then it's usually important to remind ourselves that one of the other properties says that the substring y cannot be empty, so there must be something in there. And that means that it must have at least one of those zeros. So again, we apply these two properties to argue a little bit about what this substring y is, and after looking at them, we realize that the substring y can only be in this block of zeros, and it must have at least one of those zeros. And with that information in hand, we now can make some argument about pumping this string. So let's consider two possibilities here. One of them is where we take the string y out, so we will get x, z. At this point, I'm going to do this a little bit on Scratch because I'm not sure if these are going to work. So one of them is xz. The other one is when we put an extra copy of y in there, or maybe another way of writing this, x, y, y, z. In these cases, we have different possibilities of what the string is going to look like, and we want to see, is that string going to end up still being a member of our language, satisfying our conditions on n and m. So if we are in x and z, let's look at that one. Well, we're still going to have our block of zeros. It originally had p of them in there, but because the y substring must be part of that block and we've taken it out, we've missed out on however many zeros were in the block of y, and remember that's at least 1. Now our block of ones is still of size p, and now when we look at these two values, this is our n, this is our m, we see that n is indeed less than or equal to m. So this actually is fine. This is still a member of our language, which means we're doing good. We pumped this string down and we still got another string in our language. So far so good. Maybe we're wrong. Maybe this string is, or maybe this language is regular. This is why it's important to try some things out. Again, I've got check marks here saying this worked. We're looking for something that didn't work. So unfortunately, this means overall, this didn't work. This particular example does not show that our language is, or our string is not in the language. So let's try our other one here. What happens if we change it by adding a copy of y instead? Now our block of zeros is still going to have p, but it's going to have more symbols in it. We got extras in there, and our other block is still unchanged. Now when we compare our n to our n is clearly larger than our m, and maybe I will state that here. Since p plus the length of y is greater than p, we know that this string is not in the language. This is the contradiction that we're looking for, so we're actually good. Now we pumped down and it didn't work, but we pumped up and it did work, so we're good. And it actually relied on the fact that we did have our p here being having our second block being exactly p. If we had made it larger, this argument might have been a little trickier. So we kind of got lucky with that default choice there. So let's just finish this off. Okay, so I just add a sort of concluding sentence here saying, hey, we've reached our contradiction that we were trying to do, and therefore we can conclude that our original assumption that L was regular was false. So L must be non-regular. All right, let's take a look at a second language now, another similar one. We still got a block of zeros, we still got a block of ones. We've got two variables n and m defining their size. And again, we've got some relationship between them, except this time we're saying that they're not equal to each other. That's the only thing that we've stated. So we need to start out, or at least we're going to again start out our pumping lemma argument in the same way. So let's get us started up. So we'll start with our theorem stating that L is not regular. And again, we will begin with an assumption that L is regular to reach our contradiction. And so our opening assumption, again, is usually the same. So we're going to assume that L is regular, and therefore the pumping lemma should hold. And again, that means now we get to pick some string s. So let's get started there. Let s be equal to something. Again, in our last proof, we said, hey, if we've got these variables here, we might as well go ahead and put a p in there. Let's try this out. It turns out if we put p's in for both of these, our n does equal our m. This isn't even a member of our language right now. So our built-in instinct or our default tool here, which is just plug the p's in for our variables, didn't actually work out for us. Okay, and it's actually maybe a little bit tricky for us to think, well, what should we pick here? We just need to pick some n and some m that are not equal to each other. So one of my guesses, well, I don't know, maybe put one more element on there. Now it turns out that this particular proof is a little bit tricky, and so I'm going to go ahead and, instead of trying to write the whole proof out as we're going, because we're likely to get stuck, I'm going to start us thinking about this string and ahead of the argument that we're trying to make. So remember, we're going to put this substring xy, it's going to be in this first p block. So as long as we keep this first block of zeros of size p, the one thing that we're going to be sure of is that our y string is only zeros. And remember, That's part of the key argument we've been making in a lot of our proofs so far. We get to pump those zeros up or down, and it somehow changes, from a string that's in the language to a string that's not. Now, if I'm thinking about this right now, is there some way that I can split this up, pick some y here, that if I pump it, I will always get another string in this language? The answer is actually yes. The only way that we could really mess this up is if we picked our y to just be a single zero. Because if we picked our y to be a single zero, then, bear with me for a second, if we did x, y, y, z, we would end up getting 0 to the p plus 1 and 1 to the p plus 1. And these two are equal to each other. So this would actually kind of work out for us. We could get a string. You notice this one is not in our language because they're equal. So it's possible in this case, if we picked our y in this way, that we could pump up and get to something that doesn't work. But the thing that we need to recognize here is we don't get to pick how our y is picked up. The way that the pumping lemma is said, it says there's some way that we can pump it so that it works. It doesn't say every way you split it up into x, y's, and z's it's going to be pumpable. It just says there's some way that it's pumpable. And what that means is if we changed our mind here, if instead we picked our y to be 2 zeros, then when we pumped up here, we would be at plus 2, and we would already be greater than the plus 1 over here. And the plus 1 over here will be exceeded by anything we pump up here. So if we do 2 copies, it's greater. If we do 3 copies, it's greater. If we do 10 copies, it's greater. If we do 1 billion copies, it's greater. We might think, well, what if we cut it out? Well, if we cut it out, if there's just xz, we would be still less than, we're still not equal to. It turns out this string, the one that I've just picked here, is perfectly pumpable. That means this is a bad string. It might mean maybe this language is regular. I don't know. Okay. There's a way for us to figure that out. Let's see if we can figure it out by seeing if we can come up with a better string. So one thing that came out of that discussion that we had there is that when we had a plus 1 here, if we had a string of sub size 1 here and we pumped it up, we would eventually get to a string where they were equal, and that would be a problem. But then we could avoid it by picking our substring to be a size 2. Well, if we put 2 on there now, then if we pick a substring of size 2, then when we pump up, we will hit this particular value at least once, and that will allow us to not pump with 2. You probably already recognized, and that means, well, why don't we pick a string of length 3? Well, if we can do that, maybe I'll put a 3 up there. Okay, this is an interesting idea. Notice that if we put a 3 up there, that if we pick our y to be a single 0, we'll eventually pump up to get 3 copies of it, and that will be a case where they are equal. If we pick y to be 3 zeros, if we just pump up once, they'll be equal. So that one's off the charts, that one's off the charts. But if we actually pick y to be 2 zeros, we're actually pretty good. We can skip over this 3. We can get plus 2, and then we can get plus 4. We'll skip over it. We're good. So this one's actually still pumpable with 2. So just increasing the size didn't help us there. One thing that I'll maybe mention here is right now, if we're trying to make sure that we block out 2 and 3, if we multiply them together, which gives us 6, let's try this. If we put a 6 in there instead, if we were pumping up 3 zeros, if we pumped it up twice, we'd end up with plus 6. If we had 2 zeros, if we pumped it up 3 times, we would get to 6. If we have 1 0, if we pumped it up 6 times, obviously we would get to 6. So now we can block off all of these. Notice it also would block off 6 for us, but it wouldn't do 4 and 5. How do we get them in there? Okay, well, maybe what we'll notice is we multiply them together here. What happens if we did something like this? 1 times 2 times 3 times 4 times 5, dot, 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 dot. If we multiplied this big long number together, if I had a string of 1s, of course, a string of 1 0 is going to hit any number. A string of 2 zeros will hit this because it's even. A string of 3 zeros will hit this because it's a multiple of 3. A string of 4 zeros will hit this because it's a multiple of 4. A string of 5 zeros will hit this because it's a multiple of 5, etc. We have to go up. How big do we have to make this? Well, the question we should ask ourselves is, how big can y be? What do we know about the length of y? Well, there's these two rules that we have. We have the length of y must be greater than 0. That's the one on the lower end saying it has to have something in it. But what about the upper end? We don't really say that, but we do have this other rule that says the length of x, y together must be less than or equal to p. So that means p is an upper limit on the length of y. So if we multiplied this all the way up to p, we would cover every possible length of size y. And that's the clever bit that we're going to have to introduce here. So let's see if we can put this into our proof now. So the number that we came up with was actually p factorial. So we've got our original p on there plus p factorial. Okay, this is a weird one. I don't know if this is the only proof we could do for this particular language, but let's see if we've got this one. Now, is this one is certainly in our language, since p plus p factorial they're not equal to each other. And we might mention that the length of s is greater than or equal to our pumping length, so we're good to go. So we can split our s into our three parts, x, y, and z. And remember, we were already reasoning with these ideas, so let's get them down. Since the length of xy here is less than p, y contains only zeros. Since the length of y is greater than 0, remember, can't be empty, y contains at least one zero. So again, we already were reasoning with these 2 points. They sort of were central to the reasoning we were making earlier, that y has to contain some number of zeros. But I'm going to make it very explicitly here, because it's going to become important in our argument, that we know that the length of y must be in this range from 1 up to p. Now, remember in previous proofs, we were able to pick some I that we were able to pump to. Often I equals 0 or I equals 2 works for us to pump and show that this is a non-pumpable string. But our argument that we were building for this, we can't just pick 0 or 2. It might not work for us. So we're going to have to pick another value. We're going to have to just let our I be a little bit more abstract in that we're going to define it in terms of our length of y. The critical part of the argument that we were making earlier is that since the length of y is less than p here, we know that it's going to divide p factorial, because every integer less than or equal to p divides p factorial. So that's how we're going to pick our I. We're going to let it be p factorial divided by y. And so the string we want to consider for our pumping then, based on this choice of I, is going to be x, y, y to the I, z, which you'll notice is slightly different than the definition, which might say x, y to the I, z. The reason I've done that is I wanted to leave the original copy of y in there undisturbed, and then focus our I on the extra bits that we're putting in. That's the part that we want to divide this value here. And why is that so? It's because now when we consider our block of zeros here, we're going to have the original p, because that's the x, y, and maybe whatever was left over in the z's there, but the ones that were originally there, plus these extra ones that we're going to get in here. Well, how many of them are there? There are going to be I of them, and those are going to be multiplied by the length of y, because that's how long y is. That's how many zeros are there are in each copy. This is how many copies there are. And then we're going to put on our original one here, block of ones, which is undisturbed, p times, or p plus p factorial. Now, let's just do a little bit of algebra here on the side. What is I times the length of p, or sorry, I times the length of y? Well, I is equal to p factorial divided by the length of y, all multiplied by the length of y, canceled out, is p factorial. So this must be equal to 0 to the p plus p factorial, and this must be 1 to the p plus p factorial. So those are the same, right? So this is not in our language L. So this is our contradiction. So we've reached our contradiction, and we can conclude that our language L is not regular. Okay, now let's just scoot back up here to our language here. And note that this language is, we've obviously proven that it's not regular. This was kind of a tricky argument to prove it. We had to do a lot of reasoning. We had to come up with this cool, clever p factorial term, which maybe would have been a little bit tricky to come up with. How could we get there? And this just comes with practice. So the more you practice these and the more you kind of see what the goal is, the more you're going to be able to think in with this type of reasoning. Although I do want to highlight that there is a way that we could prove this without having to go through the pumping lemma. And the way to do that is using what we call the closure property. And let's remind ourselves of one of those, and that is if you have a language L and it is regular, then the complement of L is regular. Which is sort of interesting. If we take this language L, we take the complement of it, what language do we get? There's this instinct, and this is not right, so I'm going to make it very clear, that the opposite of this language, the complement of this language, is this one. The one that we started studying out as our non-regular languages. Why? This one's saying we've got a block of zeros and we've got a block of ones, and they're saying that they're different size blocks. This one's saying we got a block of zeros and a block of ones, but they're the same size. We've taken this not equal and changed it to an equal. So if you go, not equal, that's supposed to be back to equals again. At least that's our idea. And it's certainly the idea here, and it's the idea behind what I want to argue. But in fact, this is not true. The complement of this is not this, because the complement of L are all the strings that are not in this language. And it's true that all of these strings here are not in this language, but they are not the only strings that are not in this language. There are other strings that are not in this language. For instance, this string, 101, that's not in this language because it starts with a 1 and ends with, it's out of order. Any strings that are out of order like this are not in this language too, so they would be in the complement language. That's why this is not true. But if we do something a little bit more, we just need to do one more thing. So we'll take the complement language L, and now what I want to do is enforce the order on it, saying, no, but I kick all those ones out. All the strings that look like that, kick them out. How are we going to do that? We're going to go and intersect it with another language, and that language is the one that forces the order back in. It says, take all the strings that are not in this language, but only take the ones that are in the right order, zeros followed by ones. Then what are you going to get? Then you get this language here, exactly. And now let's go backwards in our argument. Now the closure properties are still a proof by contradiction, okay? So let's go through it. Assume L is regular. Then by this closure property here, L bar must be regular. So this is a regular language. Okay, this is a regular expression, so we know it's a regular language. And again, another closure property of regular language is intersect. If I take a regular language and I intersect it with a regular language, I get another regular language, this one here. But this one's not regular. We proved it. It was the first one that we proved was not regular. So now we have to work backwards to our assumption. If this one's not regular, then that means this intersection business is not regular. But we know this one's regular. It's a regular expression. It checks out. So that means this one can't be regular. Wait, but if L bar is not regular, then L can't be regular. So our original assumption that this language was regular must be wrong. So what I've gone through here is two possible ways for us to prove this. The first being the pumping lemma, which is just, practice those skills, do them over and over again. But sometimes when you're running up against a problem like this that might be a little bit trickier for our pumping lemma, we might think, is there a way that I can manipulate this language to turn it into an easier language, like this one here, that I either already know is not regular, or that I can prove more easily with a pumping lemma that is not regular. So that's the power of the closure properties in showing things are not regular. So keep them in your back pocket as another toolkit. The pumping lemma is sort of a general purpose lemma that can be used to prove all kinds of languages are not regular, but sometimes it's easier to use a closure property tool than it is to use that general purpose tool. So let's, whenever we can, remember that we can bust out those other tools as well. All right, I hope you liked this review of some pumping lemma proofs. Thanks for watching, and we'll see you in that next video.